Hello! Hi everyone! Welcome to another lecture for Interactive Computer Graphics. So, today's topic is tessellation shaders. These are great, I love them. So, let's talk about tessellation shaders. Remember last time we talked about geometry shaders, and while we were talking about geometry shaders, I sort of mentioned the concept of tessellation slash subdivision. We touched on that a little bit. Today's topic is going to be more about this. So let's remember that. So what's tessellation? Given a triangle, I can take that one triangle and I can split it into multiple triangles like so. This is just one way of doing it. Of course, there are many ways of doing something like this. This is the operation that we call tessellation. So it's just one tessellation example. Now, why do we tessellate a triangle? Now, when I have this triangle over here, I only have 3 vertices to control the shape of that triangle, right? 3 vertices, each one having x, y, z coordinates. I have 9 degrees of freedom. Over here, I have a lot more vertices. I sort of double the number of vertices. That means I can shape this object a little more than what I can do here. So I can take some of these vertices and move them around, so give it a different shape. That's why I would like to do that. So the process of taking a triangle and splitting it into, or taking an element, it doesn't have to be a triangle, whatever, some polygonal element, taking that element and splitting it into more of them, smaller ones, is going to be the concept of tessellation. Subdivision is something that involves tessellation, and it's not going to be just about generating more primitives out of each primitive, but it's also going to include some rules about how to move these vertices around. So the subdivision also includes those rules about what do you do with these vertices after you create them, right? So a subdivision example, for example, this is Kalman-Clark subdivision. So if you take a box like this and apply Kalman-Clark subdivision, you get this. So it's tessellating each face, and also it's moving the vertices. And you apply again, you get this. You're repeatedly applying to get a high resolution model. And this is a very common way of generating polygonal models with high poly counts in computer graphics. So it's a very, very typical way of modeling. So you typically start with a relatively low poly model like this one, and then once you're happy with the shape, you apply some subdivision operations, you get more details, and then you can start shaping more details. So when you are faced with a highly detailed model like this one, if you look at it carefully, there are so many details in here. And of course, this model has lots of polygons, right? The polygonal shape looks kind of like this, right? But we don't start with a shape like this. Now, if you try to model this character was starting with this level of detail, that would be very, very difficult to do, right? So you progressively reach this level while you're generating this model typically. I'm not saying this very model is prepared this way, but there's a subdivision operation that generates this high polygonal count. So this is right before the last subdivision operation. Before that, this was the resolution. Before that, this was the resolution. So it's like you see, there's progressive resolutions, and before that, probably that was even lower resolution. I'm not saying exactly how this model was generated. I'm saying that there's this progression that typically happens for polygonal modeling, right? So in the end though, we would like to render something that's going to be super detailed. That's our goal typically. We would like to be able to render things with super high geometric detail, so they look real, right? That's the goal. That's what we're trying to accomplish. Now, the problems here is that I need a lot of compute. Well, first of all, I have a lot of pixels to shade, right? On the screen, there are lots of pixels. How can I solve that problem? I have lots of pixels to shade to generate each one of my frames, and I would like that to be as fast as possible. How can I do that? Well, I can compute each pixel. I can compute and can shade each pixel separately, independently, in parallel, right? Most of the time. So if I have enough compute here for my fragment shaders, now I can actually accelerate this process. So if I just add more and more fragment shaders to my GPU, I'm going to have computation power to generate enough fragments to form my image. That problem can be solved. So I have a high resolution image. I can just add more and more fragment shaders to just make a giant GPU chip. GPU chips are actually quite giant today. And lots of fragment shaders, I'm done. So, okay, well, before that, I need to be able to generate those fragments, right? I have this rasterizer. Okay, well, you know what? I can just split the screen and handle things differently. I can also have multiple rasterizers working all in parallel, generating all these fragments to feed my fragment shader. And these rasterizers will get the data from the vertex shader, right? So I can have multiple vertex shaders. Actually, we have unified shaders today. So there's unified cores that can execute fragment shaders or vertex shaders or any other shaders. The problem about compute, I want to have a highly detailed model with lots of triangles. At the end of the pipeline, I have lots of fragments. I can solve that with lots of fragment shaders. I can feed the lots of fragment shaders by adding lots of rasterizers. Enough number of rasterizers. I can feed the rasterizers fast enough by having lots of vertex shaders, right? So all of these things that are used on the GPU, we have lots of parallelism and it all works out fine. Now, I want to be able to push so many triangles through this pipeline, and it starts over here. So I want to be able to send these triangles really, really fast to the GPU, right? So for that, and these triangles are coming from the DRAM, basic GPU's memory. I need to have some wide connections to that GPU memory. They're all coming from the memory. But over here, I'm sort of limited. There's only so much I can do to increase this memory bandwidth. I mean, with theater, the compute and whatever, you can add more cores, you can just make your chip a little larger. I'm not saying it's super easy to do, but at least we know how to do that. But this data movement, getting this data from DRAM, it's not that easy to solve. I can just say, oh, I'm just going to add more DRAM chips. That's not a solution because it's a connection issue. That's a very, very fundamental issue. Actually, data movement is one of the biggest problems in computation performance today. And that's where we have that problem. So there's only so much I can do. I mean, I can keep increasing the polygon counts of my scenes, of my models, but when I'm rendering, I'm going to run into this problem. I won't be able to feed my GPU fast enough when I have a lot of them, because there's going to be some limit, right? So one way to get around this is using this tessellation idea. So if I send not my final super detailed model, but a relatively lower resolution version of my model to my GPU, this is going to require a lot less data to send to GPU, right? And if I could only start from this and on the fly generate more data, more elements, more triangles on the GPU, then I solve that problem of data movement. Right? So what I would like to do is to start with this lower resolution model and on the fly, on the GPU, generate this higher resolution model that I actually want to render. Right? So that's one of the goals that we would like to achieve. And tessellation will give us that functionality. So one of the reasons why we want tessellation on the GPU is solving this problem of data movement bottleneck that is very, very difficult to solve, right? So if you can't move enough data, then you try to generate your data on the fly, right? That's the solution. There's another thing though. This is not the only reason why we have tessellation shaders. There's another reason. There's another reason why we would like to do tessellation on the fly. That's the concept of LOD, level of detail. Now, the level of detail is, here's how it goes. So when I'm rendering an object like this, and it's, let's say, pretty close to the camera. I would like to see all of the details, right? But if this object is so far away, what happened now? Now, like, all of my triangles now representing this object, they're really, really small. Actually, much smaller than a pixel now, right? And I'm not even seeing all of the triangles anymore. So most of the work that my GPU is doing for rendering this is totally wasted. Those triangles are not even generating any fragments. A lot of the triangles are not generating any fragments. A relatively small percentage of them are generating fragments. So this is not ideal, right? I could probably generate an image that looks almost exactly like this, by using a lower resolution version of my model, right? And if this object is even further away, I could maybe use even a lower resolution version. So that's the idea of level of detail. So you would like to have different versions of your model, starting from low resolution to higher resolution. And not only that, I would like to be able to generate this high resolution model on the fly on the GPU, but I also would like to determine when I would like to generate this high resolution data. Right? If the object is close to the camera, yes. But if the object is far from the camera, then maybe I don't need that. Maybe what I had initially was good enough if it's far away from the camera, right? So that's the other thing, that level of detail is why we want to have tessellation, on-the-fly tessellation on the GPU, right? And we can do that with our existing pipeline that we talked about with the addition of the geometry shaders here. So this is the pipeline that we talked about last time when we talked about geometry shaders. So I have my data is coming to my vertex shader, and then it's going to the geometry shader. And inside the geometry shader, I can do this tessellation easily. So given a triangle into my geometry shader, I can just spit out a whole bunch of triangles from my geometry shader. That's totally fine. And people have done that. It works. It's great. It solves all these problems that we've been having in terms of data movement and also level of detail. But this is not terribly efficient. Geometry shaders are super powerful. They're designed to be powerful. So they can do a lot of things, yes. But everything you do inside a geometry shader is done in software. It's going to be a software implementation that runs on this geometry shader that can do all sorts of things, including tessellation. If we had something that's specifically designed for tessellation only, we could get a lot more performance out of it. Right? And if this is going to be our means of generating more data on the GPU, we're going to end with a lot of data. So we kind of need to do this as efficiently as possible. Right? So imagine this. I have one triangle with 3 vertices. From that one triangle inside my geometry shader, let's say I'm generating 60 vertices. From these 3 vertices, I'm generating 60 vertices. That's a lot of vertices to generate from a single geometry shader. But if I'm generating them one by one, that means I'm processing one vertex at a time. I sort of lost my parallelism a little bit, right? Because I'm inside the geometry shader, inside each execution of the geometry shader, I am emitting 60, let's say, vertices. So it's going to be a serial operation. It's not going to be very well parallelized because of that. Well, I could run my geometry shader in parallel with multiple invocations. I can do that. But there's going to be some computation that's going to be shared between them. I'm going to have to redo those. So like it's not going to be super optimal. And also everything that I'm running on the geometry shader will be running in software. Maybe if I had direct hardware support for common operations like tessellation, I could squeeze out more performance from my GPU. That's the idea. So for the operation of tessellation and tessellation only, we're going to have a specialized shader that's going to be the tessellation shaders. not just one shader. It's going to be plural because it's to be able to do this efficiently will require some hardware support for doing the actual tessellation operation. Also, there's going to be some stuff to control that. So actually, tessellation shader, people talk about tessellation shader as if it's just one thing, but it's actually a combination of two shaders and a hardware unit. So it looks more like this. So this is what's called tessellation shader. So we have a tessellation control shader that does the initial control. There's a hardware tessellator. There's a hardware unit that does the tessellation. And tessellation evaluation shader is another shader that does the evaluation. All right. So if these names look a little funny to you, let me show you what DirectX calls them. DirectX will call this one Hull shader and this one domain shader. So should be all clear now. You understand what they do, right? Yeah, let me get rid of the DirectX name. So we're going to stick with the OpenGL naming convention. All right, tessellation control shader, tessellation evaluation shader. So these things in total, you can think of them as like the tessellation shader component, all of them together. And they will sit between the vertex shader and the geometry shader. So the vertex shader is going to be over here and the geometry shader is going to be over there. So I can actually use the geometry shader after my tessellation. So it's not replacing the geometry shader, it's just putting a stage between the vertex shader and the geometry shader. So if you look at the entire pipeline, that looks like this. So my vertex shader will send its output to tessellation control shader. It's going to pass through this tessellator and tessellation evaluation shader, and its output is going to end up in here in my geometry shader. So obviously the tessellation shader is optional. I don't have to have one. If I don't want to have one, this data will be passed directly to the geometry shader from the vertex shader. And again, my geometry shader is optional as well. I don't have to use a geometry shader. If I don't have a geometry shader, its output is going to directly go to the rasterizer. If I do have a geometry shader, then it's going to go to the geometry shader, right? All right, so this is the overall picture, but today we're interested in this component, the tessellation related component. So let's talk about that part. Now, the general concept is relatively simple. The tessellation control shader is going to tell the tessellator what to do. So it's going to tell the tessellator, like I'm getting this triangle, its job is to tell the tessellator, you know what, there's going to be a triangle and I would like you to split this triangle, tessellate these edges and interior of this triangle using these parameters. So it's going to give some parameters to the tessellator. I'm going to talk about those parameters in detail, so don't worry about these numbers now. It's just some numbers that control the tessellation operation. The tessellator itself will generate, this is the hardware unit that will generate the actual tessellated triangle. All right? And then each vertex of this triangle, each vertex of this tessellated triangle will be sent to this tessellation evaluation shader. So tessellation evaluation shader will take each vertex of this tessellated triangle, and for each vertex, it will determine whatever it needs to do. It's basically move that vertex wherever it's supposed to go. So tessellator is going to do the tessellation operation. If I'm implementing some kind of subdivision operation, for example, that has some rule about where to place that vertex, I'm going to have to implement it inside the tessellation evaluation shader. So this is the shader where I will control where to put that vertex. So you can think of this tessellation evaluation shader as like the vertex shader that appears after tessellation. So before tessellation, I had this vertex shader before that, obviously. And its output is coming over here. And in the end, I have a lot more vertices. And each one of those vertices will be passed through this guy, tessellation evaluation shader. And this will act something like a vertex shader for those vertices. Now, the immediate question you might have is that, well, if I have this, why do I have a vertex shader in the beginning? Right? I mean, I could just do all the transformations, everything in here. Yes, I can. Yes, I can, but it's probably not the most efficient thing to do. So oftentimes it might be more efficient to transform just these three vertices in the beginning instead of transforming all of these, I don't know, a lot more vertices. So you do the transformation to your vertices early on, and then all the vertices you get here will have the transformed values, right? So you are in the correct space that you want now, so you don't have to worry about transforming them, right? So you can do things earlier in the pipeline that will make things quite a bit more efficient, and that's why we still have a vertex shader. That's one of the reasons. The other reason is that if I don't do the transformations in my vertex shader, doing level of detail decisions in here in the control shader, tessellation control shader, that's going to be a little tricky because a lot of the things that we're going to be doing in the tessellation control shader might be, if I'm doing level of detail at least, it will be related to where an object is in comparison to the camera, right? So to be able to do that, I kind of need to transform my object first before I do the tessellation. So that's why we still need the earlier stages of the pipeline. Right. But this hardware unit is at the heart of the tessellation process, and this tessellation control shader is controlling this tessellator, and tessellation evaluation shader is fixing the output of that tessellator or that hardware tessellator. So let's talk about the hardware tessellator in a bit more detail. Now this is a hardware unit. It's designed for certain operations, so it has some limits. So this is not going to be something programmable that you can do whatever you want with it. So it has going to have some limited functionality. Its input, I'm going to leave that a question mark for now. We're going to talk about that, but its output is what's important at the moment. It's going to only be able to output certain things. It's going to be able to output triangles, quads, and isolines. Okay, triangles, I think that's sort of obvious why we have triangles, or we've been dealing with triangles all the time, so it kind of makes sense that we're dealing with triangles. Quads, why do I need quads? Can I just represent each quad with two triangles? Why do I have special functionality output type of quads? That's a little odd, isn't it? Well, there's a reason for it, actually. For a lot of tessellation and subdivision operations are defined much better using quad meshes than triangular meshes. Because of that, partially because of that, a lot of the modeling operations done with polygons, polygonal models, are typically prepared as quad dominant meshes. That is, meshes that have lots of quads and maybe a few triangles. So quads are very, very useful for modeling, not all that useful for rendering. We typically take quads and convert them to triangles. Each quad turns into two triangles. But during modeling, they're very, very helpful partially because the subdivision and tessellation operations are much nicely defined, much nicer when you apply them to quads instead of triangles. That's why we want to have this specific quad primitive here so that our tessellation can be done on quads instead of triangles, because we can define tessellation in a much nicer way. You'll see that in a little bit using quads. Right? That's why we have this specific quad type. So what's the isolines? It's just a bunch of lines. So let me show you what they look like. So it's a tessellated triangle, tessellated quad. You see, it looks much nicer than this guy. This looks, well, so crazy. Well, it's crazy because it's tessellated in a funny way, but nonetheless, quads can be tessellated in much nicer ways. That's why we want to have that primitive. Isolines is another thing that's sort of easy to support, and they're very, very useful for some things. I'll show you an example later on. And isolines is just generating lines, little line pieces like this. So think of them as like quads, but I don't have these quads defined between these vertices, but instead I have these line connections. Right? So that's the other primitive that I can generate from my tessellation shaders. All right, so this is going to be the acceptable output, the only possible outputs of my tessellation shader, tessellator. Tessellator cannot output anything else. It's going to output a tessellated triangle, tessellated quad, a tessellated isolines. That's it. So what should the input be? I mean, obviously you might think, if I'm going to, my output is going to be a triangle, my input should be a triangle. If I'm going to have, my output is going to be quad, my input should be a quad. And if I'm going to have isolines, my input should be, what, lines or quad? Actually, it doesn't really matter. Because imagine that a quad like this, I can generate it without any input. I just need to know what resolution you want. I want to have a quad with, what is this? 6 by 6? Yeah, 6 by 6 quad. There you go. I mean, that's what it looks like. Yeah, the vertex positions are not right, but I don't care. This is going to be sent to my tessellation evaluation shader, which is going to place all these vertices to wherever they're supposed to go. So as far as the tessellator is concerned, it doesn't care about the positions or any data about these vertices, right? It's just going to generate these vertices and create these connections, like these four will form this quad and these four will form this quad, and that's it. So honestly, over here, I don't need any input data. I just need to know what resolution of tessellation do you want, right? That's all I need. So that's exactly what it's going to get. So the input to tessellator is going to be the tessellation information, like how much you want to tessellate. So that's going to be the tessellation levels. There's going to be an outer tessellation level and an inner tessellation level, and they're going to be defined slightly differently for triangles, quads, and isolines. But let me first talk about why do we have these two things? Why don't we have just one tessellation level? Why do we have outer and inner tessellation? Here's the thing. Imagine that I have two triangles. These are, okay, typically I have more than two triangles when I'm rendering something, but imagine that these are two triangles on a surface that may contain a lot more triangles. I'm just looking at two of them, right? Two neighboring triangles on a surface. And I'm going to tessellate this, right? So my tessellation shader is going to execute separately, independently, for each one of my primitives. So I'm rendering a bunch of triangles. For each triangle, my tessellation shader will execute separately. So for the red triangle, when I'm processing the red triangle, I decided to pick a particular tessellation level. All right? And that tessellation level was such that for the shared edge between these two triangles, I ended up having two additional vertices. So, okay, inside the interior, I have more vertices. I'm not showing you those. I'm just showing you what I ended up along this shared edge. Okay? Let's say that's what I got. And my tessellation shader also, tessellation control shader actually, ran for this blue triangle as well. And for that blue triangle, it came up with a different decision. It decided that, oh, you know what, this triangle is a little different. I'm not going to tessellate it as much. So for this triangle, I picked up a tessellation level such that the edge, the shared edge, ended up having one additional vertex in between. Is that a problem? Yeah, huge problem. Huge problem. Because as soon as I start moving these vertices, what happened here? I have a crack on the surface. I mean, yeah, obviously, I cannot generate the shape of this bent edge, the same shape with just 3 vertices as opposed to that I could generate with 4 vertices. They're not going to be exactly the same unless I strategically place them. So what's the net outcome of this? That means that I am going to start seeing cracks on my surface, which is supposed to be one solid object, right? I'm representing a solid object using this surface with a bunch of triangles, and now I have some cracks on this surface. It just totally broke all the illusion that represented a solid object. And then now it's a cracked surface, what it is. So this is completely unacceptable. We cannot possibly have this. That means if I'm going to tessellate this edge, yeah, I might have different tessellation decisions about, I might have different ideas about how much to tessellate each one of these triangles, and I can come up with different decisions for each triangle. But along this shared edge, I must have the same decision. So if I'm going to tessellate this edge into like 3 pieces by adding 2 vertices, I must do the same thing for both of these triangles. I cannot have different decisions on either side of an edge. Because if I do that, I'm going to get cracks on the surface, then that's totally unacceptable. And that complicates things a little bit. That means that I am going to decide the tessellation level of each edge of my triangle and the interior of my triangle separately. Right, that's why I'm having this outer tessellation levels and inner tessellation levels. More specifically, for a triangle, the outer tessellation level, there's going to be 3 of them, 0, 1, 2, 0, outer, 1, 2. So these are controlling the tessellation along these edges. All right? And the inner tessellation level is going to control the tessellation inside here in the middle. So in these 2 examples, I'm using the inner tessellation level for all of the edges as well. So if I use the same tessellation level for everything, I get these nice looking tessellation shapes. All right, so this is showing the inner tessellation, but the outer tessellations also use the same shapes. All right, so this is tessellation, inner tessellation 3. This is inner tessellation 4. So basically, it's just you're counting how much you would split the outer edges, but you're actually applying this to the inner part. All right, so inner tessellation. So for the edges, for these edges, I can control them separately using the outer tessellation levels. So I can just put different tessellation levels. So this is specifying different outer tessellation levels for each one of the edges. So they're tessellated differently, as you can see. Right? And the inner level is coming from here. And the tessellator will be able to get these numbers, just these numbers, and spit out something like this. And of course, it will triangulate it as well. So you'll know how they're connected in the triangulation. So we won't have to worry about any of that at all. Right? So it will form all of these primitives. It will generate these vertices, and it will send those vertices to the tessellation evaluation shader and say, there you go, there's a vertex. Now decide what to do with it. All right, so the tessellation evaluation shader is going to be responsible for placing those vertices. All right, so this is what triangles will look like. Let's take a look at quads. So here's a quad. It's the same idea. I have 4 edges now instead of 3, and I'm controlling the outer tessellation level of each one of those 4 edges separately. In terms of the inner tessellation level, now I have 2 of them. There's one that controls the inner tessellation horizontally, and one controls it vertically, or just in one direction and the other direction, right? So using those, there are different examples. So those are the inner tessellation levels. And in this case, outer tessellation levels are identical to the corresponding inner tessellation levels. And of course, I can set them separately, independently. So I can have something like this, right? The inner tessellation levels are something, and outer tessellation levels are something else. Just like in the triangle case, the tessellator will decide how to triangulate this as well. So I will know how the triangles are formed. It's just going to generate these vertices and send it to tessellation evaluation shader. Same idea for isolines. There are isolines. I have tessellation along one direction, tessellation along the other direction. In this case, I don't really need the inner tessellation levels. I just have the outer ones. So there's just 2 examples of that. And in this case, these are going to be lines. Now, you might have noticed that these kind of need to be integers, right? These tessellation levels, they kind of need to be integers. But when I'm deciding on how to tessellate something, it might be a little bit different. I'm going to be dealing with some floating point numbers. So if my tessellation decision comes from how far an object is from the camera, well, that distance, the distance of the object from the camera, is going to be a floating point number, right? And I'm going to decide which tessellation level to pick. Is it 3 or 4 or 5? So what am I going to do? Am I going to pick the nearest integer? I mean, I can do that, but the tessellation shaders are a little bit nicer than that. They actually allow floating point numbers for tessellation. So I can have what's called equal spacing. If it's equal spacing, it's going to pick the nearest integer and tessellate it using the nearest integer value. So you can provide some floating point values, you're just going to pick the nearest integer and tessellate it like that. Or you can have fractional even spacing or fractional odd spacing. That's going to generate different tessellation patterns with different types of spacing depending on what tessellation level you provide. Right? So fractional values are acceptable, completely acceptable. In fact, these are going to be floating point values that you pass to the tessellator, and tessellator will decide which one to do, well, depending on what you set, of course. That's the idea of the tessellator. It gets this tessellation parameters, and from these parameters, it's going to generate these types. Right? So let's take a look at what comes before and after a little bit more detailed. Right? So the parameters are coming in here, and these tessellated primitives, either triangles, quads, or isolines, are coming out there. So what should be the input over here? What do I send to my tessellation control shader? Well, presumably, that's probably going to get my low resolution object. So it's just if it's a bunch of triangles, probably I'm going to get a bunch of triangles, right? But the thing is, actually, what I get out of here is sort of independent of what I send to my tessellation control shader. I can get whatever I want in here and make some decision and send the parameters, and in the output could be specified completely independently. I can get a triangle as an input. I can output isolines or quads or tessellated triangles. How I specify this output is completely independent of what I send to my tessellation control shader. Because of that, the fact that this is a triangle is sort of inconsequential. Like I don't necessarily care that it's a triangle. I just know that I'm getting some data into my tessellation control shader that will do something with it. It's just 3 vertices, right? So my tessellation control shader is going to get whatever data I send to it, and it's going to decide what kind of tessellation to apply, and it will just tell the tessellator. It will just tell the tessellator that these are your tessellation parameters, right? And the tessellator will output whatever it needs to output, and it will send it to a tessellation evaluation shader. And its output is going to be, let's say it's going to be triangle, so it's going to generate some tessellated triangle based on these parameters that are given to it. And in the end, my, again, tessellation evaluation shader is getting one vertex. But it's not getting just this one vertex, because it's kind of difficult to know what to do with that one vertex if you don't have any context associated with it. So what's going to happen is that typically, we will send all this data that my tessellation control shader gets, we will send it all the way to the tessellation evaluation shader as well. So by looking at where these vertices were originally, like after my vertex shader evaluation, I can use that information to figure out what to do with this vertex when I'm evaluating that in the tessellation evaluation shader, right? And then it's going to figure out where to place that vertex, and that's going to be its output, right? So typically it's going to have access to whatever we send to the tessellation control shader. It doesn't have to. It's just going to get the output of the tessellation control shader. All right, let's be a bit more specific at this point. I think this is enough of a general idea. I think we're ready to see some code. Are you ready to see some code? Okay, let's take a look at tessellation control shader. All right, there it is. This is your tessellation control shader. Lovely, isn't it? Now, the big difference, well, not the big difference, well, the first thing that is different from all the GLSL code I showed you in this course. Look at this, core 4.1. Why? Because tessellation shaders were added in 4.0. So anything greater than 4.0 would be acceptable here if you're going to pick a core profile. Geometry shaders were introduced much earlier, 3.2, OpenGL 3.2, I believe. But tessellation shaders are here since 4.0. And this is the important bit here. It's saying that it's going to output 4 vertices. That doesn't mean that my output is necessarily going to be quads, but probably it's going to be quads, but not necessarily. So don't worry about that bit for the moment. What's important here, its job, is to set these tessellation parameters. Okay, this is the output. Now the tricky bit here about the tessellation control shader is that you might expect this shader to run once per primitive. You might expect that, and that might seem logical to you that, you know, I'm setting all the tessellation parameters for that primitive, but that's not what's going to happen. It's going to actually run, in this case, 4 times, because it's going to have 4 outputs, right? And I'm going to have this output GL out. It's like the standard output that I'm having. That's the output position. I'm going to output an output position and send it to my tessellation evaluation shader like this. So this is going to run 4 times. And with each invocation, I'm setting only one of them. Each invocation is responsible for setting one of them. But this is not necessarily how I have to implement it. The funny thing about tessellation control shaders is that, yes, this is going to run 4 times, but each execution, each instance of this for the same primitive will have access to the data of the others as well. So this is a little bit of a more complicated execution model. So am I outputting the same thing out of all 4 executions? Well, at least one of them needs to set these. The others, I don't care. So there's going to be 4 invocations of this. At least one of the invocations has to set this. What if they decide to set different values? Probably one of them will win and overwrite the other. Which one will overwrite the other? Probably the one that runs the last will overwrite the previous ones. Actually, inside these invocations, I even have access to the data of the other invocations as well. I can even have barriers in here and have thread synchronization and things like that. But typically, we don't need to have that complicated tessellation control shaders. What I'm trying to say is that this allows a lot of complexity if you want it, but typically this is something quite simple. So basically, you're going to output one output vertex. You said you're going to have 4 outputs, right? That's going to be it. And also you're going to set the control parameters for tessellation. Right? That's its job. Okay, but what if I want to send some, what if I'm getting some custom data from my vertex shader? Because my vertices have some attributes that I want to pass all the way to my fragment shader, right? What do I do with them? Well, I get them. I can get them. I actually get them all. So inside here, I'm going to get all of the outputs of my vertex shaders that run before the tessellation control shader, I'm going to get all the outputs for all of the vertices for that primitive, all of them at once. So however many. So if I'm drawing a triangle, I'm going to have 3 elements in here. If I'm drawing a quad, I'm going to have 4 elements here. So however many I have, I'm gonna have it in here, right? Okay, and if I want to send it, I received it here. If I want to send it to the next shader, that's going to be tessellation evaluation shader. I'm going to have output data here. This one is also an array, right? So I'm getting an array of values. I'm outputting an array of values, and each invocation, you could say, let's say it's going to be responsible for its own corresponding element. So it's just setting its value. So I just copied that, whatever I got, over to this one. Very simple, but not an atypical implementation of tessellation control shader. So here what we didn't do is we didn't do anything interesting about how to set these tessellation parameters. So we just picked some constant values. We're always tessellating the same amount. Obviously, if I'm implementing something like level of detail, I'm going to have to set these dynamically depending on where the primitive is in comparison to the camera and so forth. All right, so let's take a look at the corresponding tessellation evaluation shader. So this is what it might look like, not much. So here the important bits are saying, oh, I am supposed to receive some quads. So tessellator, you better generate quads for me. And I would like equal spacing and counterclockwise order. Okay, so these are the parameters that I set. So tessellator output is going to match whatever my tessellation evaluation shader expects. I'm responsible for generating the position for one vertex, just one vertex only. Think about this as very much like a vertex shader. And to differentiate that vertex from all the other vertices that I generated from my tessellator, from the tessellator generated, it's going to send me, the tessellator is going to send me the tessellation coordinates, XY coordinates, that these tessellation coordinates for the vertex. So that basically tells me where that generated vertex is on that primitive, on that quad or triangle. Where it is on that quad or triangle, I will know that by using these X and Y coordinates, right? And yeah, I don't have to set the output like this, of course. I typically won't. This is sort of not great, but I just wrote something simple here. Of course, I can get all of the input stuff is like whatever's sent to me from my tessellation control shader, I can receive it, and I can receive all of it. So in each evaluation of tessellation evaluation shader, in each invocation, I have access to all of the data, not just one, because I'm typically going to use all of the data. So I'm not going to just output one position, right? So I also have access to the 4 positions that I output from my tessellation control shader. I have access to those as well. I have access to all, I outputted 4 of them. I have access to all 4 of them. So this is just setting everything is just the first one. This is probably not great. and overriding the other one, right? So typically what I'm going to be doing is I'm going to look at multiple of them and sort of interpolate them, right? By given this tessellation coordinate, I'm going to interpolate them. Not just 2 of them, I'm probably going to interpolate the 4 of them, all 4 of them if I'm dealing with quads. And I can have an interpolate function like this. It's just doing linear interpolation along X and Y. And basically what this is doing is that given a quad like this, it's generating an output like this. Of course, the positions of these vertices will depend on the positions of these input vertices. They're defined over here, right? The very, very simple tessellation evaluation shader, not atypical. Not doing anything interesting though. It's just doing the basic tessellation operation. It's not moving the vertices around in any interesting ways. But just one way of implementing very basic tessellation shader for you. Now the important bit here is to understand that I have access to this data in here, to all of the data that I need, everything at the same time. And over here I have access to all of the data plus the one vertex that I'm supposed to modify. All right. Okay, so all this part is, I'm hoping, clear. Now let's drill down on this bit a little bit. I'm getting 3 vertices. Does it really mean anything? I mean, what, does it have to be 3 vertices? Because the output here is completely independent of what I sent here as input, right? So I'm setting the output from the tessellator, and it's sort of set completely independent of what this input is. So do I really care what this input is? I don't actually care what it is. I just need to send some data, some amount of data, some number of vertices to my tessellation control shader. And oftentimes when I'm doing interesting tessellation operations, I may need some neighborhood information and whatnot. Remember when we were talking about geometry shaders, we had different interesting primitives. We have triangles with adjacency and stuff like that. We're not going to have that complexity here in tessellation shaders because tessellator does not care. It's going to throw away whatever primitive you had before, and it's going to generate its own primitive. It's going to be one of these, right? So, doesn't care. That means I don't care. Let's call it something. Let's call whatever you're going to generate a patch. Good enough? What's a patch? I don't know. You tell me. I say a patch is something with n vertices. What is n? I decide. Okay? I decide. I'm going to specify what n is. Of course, there's going to be a maximum that's going to be permitted, but I can specify it to be whatever I want. So I can define my own primitive type and process it however I like. And when I'm drawing these primitives, I'm going to have this patch primitive. I say, gee, I'll draw arrays, my patches. And because I call this one first, it will know how many vertices per patch it needs to send through first vertex shaders and then into a tessellation control shader. So my tessellation control shader over here will receive the entire patch. So this n will typically match the n over here, right? And I'm going to output n vertices, and I'm going to send all of them to my tessellation evaluation shader. My tessellation evaluation shader will receive my entire patch, and then we'll decide what to do with it. Right? So that's the whole idea. It's actually quite flexible structure. Right? You can do all sorts of interesting tessellation operations. Now the tessellator itself is fixed function, so what it can do, the hardware tessellator, what it can do is limited, but how I control that and then how I decide where to place my tessellated vertices, there's a lot of flexibility there. So I'm just going to show you a few examples. So this is the extent of the tessellation shaders discussions that I had in mind. So that should probably give you an overall idea about how to write a tessellation shader. But of course, things get interesting when you start thinking about how you could use the tessellation shader to do interesting things, like how you could get a sort of low resolution model like this and then generate this high resolution super detailed model. In this case, in this example, you could see that with tessellation shaders, we're adding a lot more geometry, and with that geometry, after we generate those additional vertices, we can modify them. In this case, we have these spikes that are extruded off of the surface. Over here, without tessellation, I don't have that geometric capability to generate these extrusions. In this case, I do have them. These spikes are coming out, right? So you can get some nice looking images like that. This demo actually. It's been more than a decade, I believe. It's 2009 when it came out, something like that. Another example from that era. This one was about hair rendering using tessellation shaders. So if you look at this hair, there's so many hair strands, and all the hair strands are curved and all. There's so much vertex data in here. You probably don't want to send all of that, and you want to generate it on the fly on the GPU, and you can do that, and that's the idea. You just send some of them that define a curve, and then based on that curve definition, You can generate individual vertices that generate this curved shape, and then from that you can generate those isolines, right, with a tessellation shader, and then you can place each one of those isolines independently, and you can have a complicated hair shape like this. We have used it in my group. My student Kuyu, we implemented a fiber level cloth rendering method. So if you look at it, if you zoom in here, they're not just yarn level details, they're fiber level. They're individual fibers of yarn are displayed in here, and we can do that using tessellation shaders. This work is heavily using tessellation shaders. There are more than 100 million fiber curves. 100 million curves. Each curve has individual segments, however many, it's controlled. So there's so many lines in here. And we can do that, we can render this real time. Like if you look at it, there's so much geometric detail. And we can do that in real time because we're generating all this data on the fly on the GPU. And that does make a big difference in the appearance. You can see that's these two examples. These fiber level geometric details are very different in here. So one of them looks quite more fuzzy than the other one, right? So there's a yarn level simulation that's rendered on the fly in real time on the GPU. All right. So that's what I plan to show you for today. But you know what? I can actually, let me do a little bit of a demo of what we're going to be doing in the upcoming project. All right. So this is going to be our next project that will involve tessellation and geometry shaders. So with the tessellation shader, what we're doing is that we're taking just one quad over here and we're splitting into a whole bunch of triangles. Let me show you the triangulation. You see we're generating all these triangles and we can modify these vertex positions independently. And we actually have this geometric detail properly rendered on the GPU. And you can, it's actual geometric detail, so you can compute shadows for it, you can shade it, you can do whatever you want with it, right? This is actual geometry. But what we're sending to GPU is just one quad. And out of this quad comes a teapot. So that's the idea for our upcoming project. And over here, this is all done with the geometry shaders. What we're going to add on top of that will be, sorry, this is all done with tessellation shaders, no geometry shader here, no need for a geometry shader. But we're going to add the geometry shader to display the triangulation here. So geometry shader captures the output of the tessellation evaluation shader. So it gets all the tessellated primitives before they're sent to the rasterizer. And in this case, it's capturing the output of the tessellation shaders right before they're sent to the rasterizer. And then it's converting these little triangles into line segments, and that's how we're displaying this wireframe on top of this model. Okay, so this is the demo of our upcoming project that we will be, that you guys will be implementing next. All right, so this was the plan for today, tessellation shaders. I think you guys have all the information that you need for implementing this. Next time, we're going to be starting the second half of this course. Starting next week, you guys will know your final projects and you will be working on those. What I will be doing is that I will be talking about all sorts of advanced stuff. So what we did in this course so far was to give you all the fundamentals of the tools that we have for interactive computer graphics. more specifically, real-time rendering on the GPU. Now, in the rest of this class, we're going to talk about what to do with those tools. So I'm going to talk about all sorts of advanced techniques that we use for interactive computer graphics, and we're going to discuss them in a relatively high level. So those discussions, these lectures are going to be very different than the ones that we had so far. The upcoming lectures will be more like high-level discussions of some ideas of how to use this GPU functionality to do all sorts of interesting things. I'm not planning to show you much code, if any. Those are just going to be high-level discussions. We're going to talk about advanced topics, but some of those topics will be cutting edge, like really bleeding edge stuff that just came out recently. Some of the stuff is going to be really old stuff that still applies. Actually, we're going to start with an old stuff that still is really applicable today next time around. So be prepared that the upcoming lectures are going to look probably quite a bit different. This is, I believe, where we completed our discussion of the fundamentals for interactive computer graphics. And I'll see you when we're talking about the advanced stuff. Thank you all for joining. I'll see you all next time. Bye.